Chapter 3.7, Optimization Problems, Day 1. Optimization is very much like related rates. I'm sure you're all delighted to hear that, and that it's a pretty hefty application of calculus. All right, so as you're doing these problems, there's several steps that will help you do better at them. The main thing to realize when optimizing, you're going to look for a max or a min. Optimize means find an extreme, looking for a max or min. All you're going to be looking for is to set up a problem to use the first derivative test. Today, we're going to look at the steps to help optimize. We're going to do one problem, and that's it. We'll do more problems tomorrow. So first off, the steps for optimization. There's 5 guidelines. I would hesitate to call them steps. 5 guidelines. First guideline. Assign symbols to all quantities, both given and to be determined. Make a sketch of able. So everything you know and you don't know, give it a variable. Say, okay, x equals this, y equals that. If you're talking height, call it h. If you got a circle, make a radius. All right? Step 2, make a primary equation. This is very important. Write a primary equation. So all these questions are going to say, what's the maximum profit? Or what's the minimum cost? Or what's the largest volume possible given this situation? That's your primary equation. When you write a primary equation, look for the words maximum, minimum, largest, least. And that's the equation you write. Very often in your primary equation, there's going to be more than one variable. You have like cost equals x times y plus 5. Okay, that's not a good situation. When that occurs, you're going to want to write a secondary equation. All right? In your secondary equation, the purpose is to get rid of the variables. So you want your secondary equation to be related to your primary equation, or one of the variables in your primary equation, so you can use it to get rid of it. Right? Once you've gotten rid of extra variables in your primary equation using your secondary equation, you're going to determine the domain of your primary equation. This is a lot simpler than it sounds. You're just going to see, okay, what makes sense. If I'm talking maximum volume, it doesn't make sense to use negative numbers. It doesn't make sense to have a volume way out there at 1 million when you're talking about a cardboard box made out of a 8.5 by 11 sheet of paper. Right? So look at what makes sense. Don't look at negatives when you're talking volume. Don't look at negatives when you're talking costs. And then finally, determine the desired max or minimum using the first derivative test. All right? So let's look at our one problem for today. First step, assign variables. They drew a picture for us. They tell us that a manufacturer wants to design an open box having a square base and a surface area of 108 square inches, as shown in the figure. What dimensions will produce a box of maximum volume? Well, we have a square base, so our base is x squared. Our height is h. They assign those for us. What dimensions will produce a box of maximum volume? So our primary equation is going to involve volume. So our primary equation must be volume equals, now as I take a look at it, it's a box, length times width times height, but the length and width on the bottom, they're both x, so it's x squared times h. That's what I want to optimize. I'm going to label that is primary. Now because there's an x and an h, there's nothing I can do with it right now. I need to come up with a secondary equation that involves h in some way. What other information do they tell me in this problem? Well, they tell me the surface area is 108 square inches, right? My secondary equation will involve surface area. So surface area, what is this surface area? Well, this is an open box, meaning there's no top, but I get the other 5 sides. The bottom is x squared, and then there's 4 sides that are all x times h. So my secondary equation is surface area equals x squared plus 4x times h, knowing the surface area is 108 square inches. So 108 equals x squared plus 4xh. Now, I want to solve my secondary equation and put it into my primary equation. So I want to look and I want to say which variable is easiest to solve for. There's either x or h. Looking at it, I see x squared plus 4x. If I want to solve for x, I need to use a quadratic. I also have an h hanging out there. There's just one h. That's the one that's easiest to solve for. So I will subtract x squared and divide by 4x. So h equals 108 minus x squared over 4x. Now I'm going to substitute that in. My volume equals x squared times 108 minus x squared over 4x. Let's clean this up a little bit so it's easy to work with. I have x squared here, x on the bottom. That'll cancel to just x out front. If I distribute that x out front, I get 108x minus x cubed all over 4. I can split that, 2 on 1. 108 divided by 4 is 27. X minus 1/4 x cubed. That I want to optimize. Okay, let me do the optimization on another page. So again, domain range. What makes sense for a domain? Well, definitely nothing less than 0 because it's volume. And because the surface area is 108, I'm not going to want something too much larger than that. If I look at 108, that should keep me to a pretty smaller box. So nothing like no x values larger than maybe 10. That would give me a base of 100. So x will be between probably 0 and 10. All right, so let's differentiate. Find the rate of change of volume with respect to x. Give us 27 minus 3/4 x. Find your critical number. Where is that equal to 0? 27 minus 3/4 x equals 0. 3/4 x equals 27. Divide by 3. Multiply by 4, or multiply by the reciprocal. This cancels to 9. X equals 36. All right, so 10 was probably a little off. Oh, x squared equals 36. So x equals plus or minus 6. We already talked about it's not negative 6. So x equals 6. Let's make a sign chart to check it off. So the derivative between 0 and 6, if I stick 1 into this equation, get 27 minus 3/4, that's positive. So it is increasing into x equals 6. If I stick 7 in, 7 squared is 49. 3/4 of 49. is 36.75. 27 minus that is negative. So we have a relative max volume when x equals 6. If we go back to our question, what are the dimensions? Well, x equals 6. H equals 108 minus 36 divided by 24. So 108 minus 36 divided by 24, H is 3. So the dimensions of the box are a square base of 6 by 6 with a height of 3 will give us the maximum volume when the surface area is 108 square inches. So again, reviewing the problem solving strategy, come up with some variables. Right? Assign symbols to your quantities. If necessary or possible, make a sketch. 2, primary equation. Keyword, look for what's max or min. Your primary equation will likely have more than one variable. Write a secondary equation to get rid of it. You got your primary equation, you got your secondary equation. Determine a reasonable domain. Again, look at the application, look at the situation, what makes sense. A lot of times, negatives don't make sense in some of these situations, particularly if you're talking about volume. You can't have negative volume. You can't have negative cost. You can have negative profit. So if it's a profit situation, be careful. And finally, do your first derivative test to find your max or your min.